All right, guys, so we've done the great majority of the theoretical heavy-duty lifting already. We've taken a look, defined the phasor, took a look at how to turn the IV characteristics for the resistor, inductor, and capacitor into phasor form. It was a very simple relationship. They almost all looked like Ohm's law, except now we have the frequency domain analog of resistance to cover both the inductor and the capacitor, namely the impedance, right? So we also talked about very briefly what Kirchhoff's laws look like in the frequency domain. And now there's not very much more heavy-duty lifting that we need to do theoretically. We can actually start defining equivalent circuits, and we inherit all of the results that we developed very rigorously in the third chapter of the book, where we took a look at simple resistive networks, as well as the fourth chapter of the book, which was on techniques of circuit analysis. So right now I want to turn my attention very briefly to defining impedances in series and in parallel. And one of the things that's going to be very, very pleasant is you're going to see they follow the same mathematical form as that for resistances in series and in parallel. So here let's actually talk about series and in parallel simplifications. And I'm going to tack onto this in the frequency domain. And the first thing that I want to talk about is the representation of impedance. We know that resistors themselves are represented with a circuit element that looks like this. Inductors look like that, and then capacitors look like this. In the frequency domain, all of these are replaced where they're impedances, and the impedance is given a black box with the letter Z inside. Remember that for a resistor, the impedance of the resistor is simply the resistance. For an inductor, the impedance of the inductor depends on the frequency of the input signal, and it is calculated through this formula, J omega L. And lastly, for the capacitor, the impedance of the capacitor, whoops, let me erase this very briefly, is 1 over J omega C, like this. Right? So let's talk about series impedances. For a network, of impedances, and again, these could be capacitors, they could be inductors, they could be resistors. The only thing that's important here is that they all be connected such that the current flowing through all of them is constant. So if we have a set of inductors like this, right, notice that there are quite a number of nodes here. And if there is a current, a phasor current that's flowing through one of them, that same phasor current is going to flow through all of them. So what defines these impedances in series is that the current, phasor current here flowing through all of them is constant. If that's the case, then we can actually replace, by equivalent circuits, the entire network of impedances with a single impedance whose equivalent impedance is the direct sum of all of the individual impedances like this. This is an important enough result to box. That's what we were actually looking for. And you can imagine, based on our discussion, that we're going to do something very similar for parallel impedances. So here the picture that we actually have is, suppose that we have a network of impedances such that they are all connected like this. Let's make the drawing a little bit prettier, like this. Suppose that this is an impedance Z1 all the way up to Zn like this. Now, if there happens to be a phasor voltage across this, then by KVL around every single last one of those loops, one of the things that you can conclude is that this phasor voltage for all of them is constant. Now, if that's the case, then this network of impedances, which could be capacitors, inductors, or resistors, you can replace with a single impedance such that the reciprocal of the equivalent impedance is equal to the sum of the reciprocals of the individual impedances in the original network. And you'll see that this becomes extremely useful. This is useful enough to box, and we'll see various examples in which we can actually use this to great advantage.